Okay, so this is where we stopped yesterday. So we've looked at this important thing. I'll repeat this one because it's really important. So the fact that what happens when we multiply signals. Okay, so essentially there's three cases. First case is we multiply a signal with a fixed number. Okay? If we multiply with 1, all the samples stay the same. If we multiply it with 0, all the samples become 0. 0.5 is going to reduce the gain. Any negative factor will invert the signal. Okay, that's fairly straightforward. Now, if I multiply with a slow signal, sub-frequency, sub-audible frequency signal, then I get the modulation, amplitude modulation. And this is what we've looked at. We've looked at the fact that if I have a bipolar modulator, means -1 +1 range, then I get ring modulation, which means that the original signal disappears. If I multiply with the unipolar signal, this is what you see here, so I've changed the range of the signal. So after that, it's going to be between 0 and 1, so it's a unipolar signal. If I multiply with that, then I will retain the original signal. And what I get in both cases are sidebands, okay? So this is what we've looked at. So in this case, I'm multiplying with a unipolar signal. Therefore, this is AM, amplitude modulation, not ring modulation. And in this case, the original signal is still there, and I get two sidebands. So these sidebands are some frequency and difference frequency. So if this is 500 hertz and the modulator is 200, then this will be 700 and this will be 300. Yes?
What will happen to square wave?
Very good question. So the square wave you can consider, in this case, it makes sense to consider it as a sum of sine waves. Okay? So a square wave has no even harmonics, only odd harmonics. So let's say I have a 300 hertz square wave. It means I will have high energy at 300 hertz, nothing at 600, no even harmonics, but I will have the third harmonic 900, but with a lesser energy. And then the fifth harmonic, 1500, even lesser energy. As you know, the square wave will have odd harmonics with decreasing amplitudes. So actually you do the same math for each of the harmonics. And that's what you get. So you will get this shape, this kind of side-banded frequency for each harmonic and progressively smaller. I mean, obviously, that's a good practice to kind of to talk about that and specify it, you know, in good English, I hope. But obviously, one of the things we can do is just make it a square wave and verify. So actually, as I said initially, this first half is theory, but a lot of theory is usefully verified by trying it out. You know, so especially in the learning stage, you really want to try things out. Okay, so this is my modulator, and then you see this is what happens. So if I just slightly increase the frequency of the modulator, you see what's happening. I mean, in essence, this is a linear plot, so it's not very helpful. But if I pull it all together, you see, if I make the modulator very small, right? Oh, sorry, I'm doing it the wrong way around. So I'm making a square wave modulator. However, the math is the same. It's just that in this case, this one was the unipolar. So I'm not going to get into too much detail there. But if I modulate a square wave, I think this is the one that I wanted to show you. You see, that's what happens. So for each harmonic, you get a set of sidebands. And you see how the modulation frequency actually distances the sidebands as you increase it. Okay? Great question. So actually, and from that, you see, you can now imagine what happens to any arbitrary signal. Because you take the spectrum, the original spectrum. In the case of AM, you have the original, and you just make two duplicates, and they go apart like that as you increase the modulation frequency. Okay?
Interesting that you firstly changed the modulator to square wave,
Yeah.
and at some point when you decrease the frequency, it looked like a noise on the spectroscope.
Yes, because you see what happens there is that now I'm having a if I do that, I can do that again obviously. Because then actually this acts as the carrier. So in the terminology, technical terminology, we call this the carrier frequency, this one, and this one is the modulator frequency. Okay? So if you think about what's going to happen there. So what you're saying, if I have one carrier and I have a sine wave modulation, I get two sidebands. Now, if I have a square wave modulation, then each of the harmonics of the square waves will act as the next modulator. You see? So what will happen then, if let's say the square wave, let's do this. I mean, you can try to verify that as well. So if I have this at 100, or let's do something, it's not very visible, let's take 300. Okay, so you actually see, I mean, there is some beating. This is due to interference between certain frequencies. But what you actually see that I have a single carrier at 3K, but I have a lot of sidebands. Because each of these sidebands corresponds to one of the harmonics. And because the harmonics are progressively softer, therefore the sidebands are also progressively softer. Make sense? And then if I really decrease this frequency, you see then the sidebands, there's increasing amount of sidebands, I should say number, increasing number of sidebands. And you understand that, for example, if I have a modulator at 5 hertz, it means that I have a sideband at +5, at +15, at +25, at +35. So actually every 10 hertz, I will have a sideband progressively softer, and that's why you see that it kind of flattens the spectrum out. How does this sound? So you actually hear the 5 hertz coming through.
Yeah.
Because actually what's happening as well, I mean, I think I will tell you something a bit more complex now, okay? And then I will ask you, do you want to go that far? But, you know, it's even if you don't fully understand it now, it's useful to just know what there is to know. And if you need it at any time, you know what to look up. But actually, spectral analysis, you see, this is a spectral analysis in front of us. It does not work with filter banks. Okay, you've heard the concept of a filter bank? When you have a lot of filters, a lot of bandpass filters, like a graphic EQ, right? It's a bit like a filter bank. So initially, the spectral analysis did use a filter bank. And for every filter, you get an energy, an amplitude estimate, and that's your spectral analysis. Now, FFT does not work with filtering. Okay? It's a very optimized algorithm, which is actually not great. And the reason it's not great is what I've talked about yesterday, because you don't want to represent impulse with sine waves, and you don't want to represent noise with sine waves. So actually, we do have spectral analysis, which separates sinusoidal components, impulse-like components, and noise-like components. And if you do that kind of spectral analysis resynthesis, the results are much better, especially if you do processing. Because, for example, if you want to stretch a sound and you start stretching an impulse-like signal, you're going to mess it up. It's going to change the timbre. It's not going to sound right. If you start stretching a noise-type signal, right, you will actually lose the density of phase randomness because you're stretching it. So what you'll get is instead of a rich noise, you will get this FFT type cheap MP3 noise. Okay. So actually, that's useful to know that there are better FFTs, better spectral analyzers than FFT. Okay, so what I want to tell you about FFT though, so it does not work with the filter bank. It actually works with multiplication. That's why I'm bringing it here as a more complex thing. Because what happens if I take a sine wave and I multiply it with itself? Actually, in fact, I can just do this. The sine wave multiplied by itself. If you can reason this, you're the best student, because actually you already have the tool, because you know what will happen with the sidebands. Okay, so what sidebands do we expect when we multiply two sine waves? How do we calculate them? You multiply the sine waves, and you get a spectrum with sidebands, but you don't calculate the sidebands with multiplying, you calculate them by, I've already said today and yesterday. We might be getting too complex, it seems. I have to get the feel for you guys like that. You get sum frequency and difference frequency. You remember, I just said the example. If I have a 400 hertz sine wave, I multiply with 100 sine wave. The resulting spectrum consists of sidebands which are 500 or 400 plus 100 and 400 minus 100. Those are the sidebands. 1 plus, 1 minus. And the distance is always your modulator frequency. Right? So if I increase what you saw me do, I increase the modulator, they go further apart. Right? So now, what happens if I square a sine wave, if I multiply it with itself? The same thing happens, because it's math, obviously. What is the sum frequency? If I have a 3000 here, what is the sum frequency?
0 and 6000.
Yes, those are the two frequencies. So the sum is 6000, the difference is 0. 0. What is 0 frequency? Yes, but what else? It's actually what we call DC offset. Okay, you might have encountered this term before. So DC offset means that I essentially have an unbalanced bipolar signal. So the signal is bipolar, it goes plus and minus, but the middle is not at 0. It has a DC offset. So you know the terms DC AC, AC DC, alternating current, and direct current. So the fixed voltage. Okay? So DC offset means I have a fixed voltage in the signal. Right? I don't have a clean AC signal. It's not centered around 0, but it's offset. So it's DC offset, there is a voltage, a fixed voltage in the signal. So actually, that's what happens. If I square a sine wave, I get double frequency, I get the octave on top, and I get a fixed voltage. And this is how FFT works. Because if I have a complex signal, my speaking voice, and I multiply it with 3000 hertz sine wave, the amount of fixed voltage is the amount of original 3000 hertz content. You see, because all the other frequencies in the complex signal will move around and create sidebands, but only the 3000 will make a fixed voltage, will make a DC offset. And that's something that we can detect much easier, you see? So actually it's really interesting how, it almost like resonates into the system, and wherever it meets with itself, right? As much as there is 3000 hertz in the analyzed signal, that much fixed voltage I will get out of the process, and then I can measure this fixed voltage, so I know how much there was originally from the 3000 hertz in the complex signal. Okay? So this is a bit more like, okay, well, who knows if will I need this? But I think it's really useful because, we are laying foundations. I'm not, as I said yesterday, I'm not interested in showing you turn this, sounds like this, turn that. We want to lay the foundation, understand the signal processing. There is a lot of math in there. It's simple math, but there is some. And a bit of kind of programming, okay? So we're going to be using Max MSP, which will allow us to test these basic ideas. Okay? Rock on. Any questions? Cool. Stop me at any time. I'm very grateful that you ask questions. That's great. Okay, so the next chapter is FM. Okay, you've heard of FM, it's frequency modulation. So how is that different? So in Max MSP, what we have to do is control the frequency of one sine wave with another one. Okay, so in essence, if you're a visual learner, and everyone is a visual learner, FM, you can say, arranges oscillators vertically, whereas what we've done yesterday and what we began with, we arrange oscillators horizontally. Obviously, that's just a matter of graphical display, but actually mentally, it's a really good image to remember, because you see, in AM and RM, we've multiplied the sine waves together, so they're horizontally arranged. And in FM, we're not going to multiply the sine waves. We're going to make one sine wave control the other one. Okay? So the thing to understand here is that we have to deal with signal range. Okay? So that will be range conversion, which is a bit of math, but it's definitely useful to fully understand. So the thing that you might know is that in digital domain, our audio signals go between -1 and +1. Okay? Now, sometimes you want it to go in a different range. So that's range conversion. You just change the minimum and the maximum. You have the same signal, but you move it up or down, which is addition, or you scale it, which is shrinking it and growing it like this. Okay? So those are the two things that happen. Now, in order to produce an FM, what I need is I need the modulator signal, so this will be my modulator, to have a different range. You see, because if I just do this, if I just connect my modulator to the carrier, the values coming out of the modulator are between -1 and +1. So this means that I'm going to have the oscillator, the carrier, go between -1 Hertz and +1 Hertz, because that's how it gets interpreted. Every number coming from here will become the frequency in Hertz. Okay? So, and that is obviously inaudible, -1 and +1 Hertz. So I obviously want something that is audible. So what I need to do is I need to change the range of this signal. And as I said, I can grow it and shrink it with multiplication. So I will multiply it with 100. Okay, so if I multiply with 100, then from here, I will get the range between -100 and +100. Now that can still be quite uncomfortably low in terms of frequency. So what I shall do then is I will shift this range up, and I will add 1,000. Okay, so then at this stage, the signal will go between 1,100. Perfect. Okay, so at that stage, I can actually observe what happens. Okay, so in Max MSP, you see, I didn't specify the modulation frequency here. And this is what happens. Okay, so I'm going between 900 and 1,100 Hertz. And I'm going up and down at the rate of 4.8 Hertz, which is about 5 times per second. Okay? So you might know this, but it might be a lovely surprise that if I increase this frequency, I get an FM sound. So what you've heard and what you've seen is actually a very similar thing, sidebands distancing from the carrier frequency. And actually, the difference is that we have higher order sidebands as well, right? So in RM and F and AM, you saw we had a single pair of sidebands, but here I have another pair as well. And actually, I do have another one, only it's not displayed. So we still have the sum and the difference frequencies, which is what we call first order sidebands. But we also have second order sidebands, which will be a factor of 2 in there. So it will be 2A plus B, 2A minus B, 2B plus A, and 2B minus A. And there is overlaps there, but at least, you get all the combinations, so to speak. And they're progressively softer. So at some point they're inaudible or not detectable, but technically, mathematically, we have an infinite amount of sidebands coming out of an FM scheme. Okay? So it's the same math, sum and difference frequencies, but there are multiple sidebands. So now actually you're probably asking the question, what happens with the square wave? And the reasoning is the same, right? So if you have a square wave as a modulator, you can think about having an infinite amount of modulators progressively softer, which are the harmonics of the original. Okay? If you have a square wave in the carrier, then for each harmonic that you have, you will get a set of infinite sidebands. Okay? So, and that's the power of FM. That's why it was one of the most popular synthesis types until the 80s pretty much. So all of the 70s, it was all FM really, because you know, in the 70s, an oscillator was very expensive. A single oscillator was not cheap, okay? So with this scheme, using 2 oscillators, you could already get really complex sounds, really complex spectra. Okay, so I've started the talk with explaining how in Cologne, early days, in the early 50s, they had a few measurement apparatus and oscillators, filters, noise generators, but only a few. And these are sounds which are very simple, and you get bored after a while. So actually this was one of the ways of creating really complex timbres. It was the only way back then, obviously electronically, synthetically. Is that cool? So what happens if I use a noise modulator? That's an interesting one, okay? So what I will do here is I will take a noise, and I believe that this one doesn't work, so I can... Well, actually, let's just first hear the noise, and then I'll introduce another element. So what you hear is kind of underneath, yeah? So what happens actually in this scheme is that this multiplier, right, controls the range of the noise, and if I increase that, you see I get much more noise. Okay, technically it is going now the oscillator, you see, it receives values here. It receives values between 0 and 2000. You see, so it's actually jumping around much more. Do you guys know how we synthesize white noise? How is it produced? So white noise, you know how it sounds, right? it is actually random sample values one after the other. Every sample value in white noise is a pure random number. Okay? So actually what I'm doing now is I'm having an oscillator jump up and down randomly between 2000 and 0 hertz. But what I can do as well, maybe I have to remember, is it latch is in Super Collider, I remember, yes. SAH, yes. So sample and hold, you've heard of this one? No? So sample and hold is another very early available tool in synthesis. And it's essentially a bit like an A to D converter. You know how an A to D conversion works? Not much, yeah? So actually I'm jumping over some really important fundamentals in the meanwhile. And I will give you all the books. I will try to, just talk about the most interesting things, because my goal here is to motivate you to read the books, to try it out, to get going. My colleague in Bristol, he just told me an amazing metaphor, because in England, students tend to complain. They feel they're customers and they have demands, not like here. You cannot complain here, Here I'm the boss. There, student is the boss. It's slightly different. And, they're like, yeah, but I didn't, I did the whole course and I didn't learn much. And he says, well, the university is like a gym membership. You pay that you have the tools, that you have a personal trainer, but if you don't work out, you're still gonna stay fat, So you cannot complain after that, oh, but I still don't understand. Because you have everything that you need and you have to invest a lot of work, right? So my task here is obviously to be available. They already know I live in the UK, so I will be online until April. We're going to have some sessions online. So I will be available, but you have to work out. If you don't work out, you're not going to get strong. Never. No matter how good I am, no matter how expensive the stuff is, you're not gonna. So, work out. So my point is to motivate you. So I'm typically selecting the most exciting kind of, oh, really? Kind of things just to get you motivated. But you will have to, look through the books. Through the books these days, right? And identify things that you don't understand and read it. It's your workout, You are building your own brains. I cannot do it directly. So sample and hold. So I'm jumping. I just said this, is that you understand that I'm jumping over sampling theorem, because it's kind of boring. Kind of everyone knows it. There is not much inspiration you get from understanding, Nyquist theory. But, if you say, okay, I'm interested, I want to have a technical understanding of these things, you have to go back and read these things. Okay, so sample and hold, what it does, it has two inputs. Okay, so in Max MSP, these are the inputs. These are the outputs. You might have multiple. That's fairly intuitive. And then if you hover over with your mouse, it tells you what it is. Okay, so this one is values to sample, and this one is trigger input. So what happens with the sample and hold, in the left inlet, you can give it any signal. In the right inlet, you give it a trigger, which is like tick, like an impulse. Tick, tick. And every time it receives a trigger, it will hold the sampled value. That's why it's sample and hold. So when it receives a trigger, it takes the value from the input and keeps it fixed. So it holds the input value until the next trigger, and then it makes a quick jump to the next value. Okay, so if you put a sine wave into sample and hold, we can do this as well. By the way, in Max MSP, unfortunately, the scope is not great. It takes some time to get friendly with it. By the way, there are newer solutions now with Max for Live, and it's all kind of getting somewhere, but I'll show you one anyway. So what I can do then I can take a sine wave. I'll take a low frequency sine wave like that. And then I will take, well, actually, the trigger is any signal. Actually, you can put in there. And the trigger is defined as a zero crossing. So when the signal crosses the zero line, and typically from negative to positive, you are interpreting a trigger. So actually, I can use a sine wave for the triggering as well. But actually, what I will, well, I can do that. I will do an odd, let's do a 57.89, because I don't want them to have a harmonic relationship. And then you get something like this. So the scope is such that I can actually make some settings. Let's do this. You see? So it's a kind of a sine wave underneath, but I've done a sample and hold. So I've made it a staircase signal, so to speak. You can also try to listen to that. It's going to be a heavily distorted sine wave. And maybe some of you can guess. That's it. Where you have this process, because you've probably used it already.
Distortion.
Yeah, so you have the two digital distortions that we have as a starting point are the bit crushing and the resampling. So this is the resampling. I'm effectively reducing the sampling rate really low. And it already sounds a bit like a Commodore or whatever. I mean, if I do this on a slightly higher rate, let's do something like 87. Okay, so I have more of a sine wave coming out. It kind of sounds like an old console already. Okay, so this would be resampling. So I'm effectively reducing the sample rate. And what would be bit crushing? You guys know? Well, bit crushing would be also making a staircase, but not by imposing a lower sample rate horizontally, but by decreasing the grid vertically. So the vertical grid becomes less detailed. So where you used to have a curve, you will have a jump. Right? So you just reduce the resolution vertically. So actually both processes are resolution reduction. Resampling is horizontal resolution. Bit crushing would be vertical resolution. Okay? So that's why they are digital distortions, but actually sample and hold was available from the early days of electronic design. So you could do this kind of signal processing in the 50s and probably earlier as well. At least they started in the 50s. Okay, so that's sample and hold. Understood? Now what I can do then is I can take this sample and hold in order, I shouldn't have actually deleted all of that, and actually process my noise signal. Okay, so if I do this with a noise signal, I still have a noisy signal, so it is random values, but they come much less frequently. So what I can do then is say, well, actually, what I'm going to do is I'm going to use this sample and hold noise for my modulation signal instead. Right? So I've just inserted that sample and hold there. And I've lost my speaker, it seems. Sounds like the 60s, 70s, yeah? Easy. Okay, so what happens now is you see that I have actually it's a single, again, I have only two oscillators. I have a noise oscillator, typically they call noise generator, and a sine wave oscillator. I have another component which is sample and hold. But I can actually get something that sounds very rich and dense and a bit like early sci-fi movies, right? Because that's what they've done. And now I can show you what happens if I play with the frequency of the sample and hold and the frequency of noise. You see, because now I have an extra parameter here. So if I increase this noise frequency, you see you can't really hear much happening because it's already random values. Oh, sorry, I'm talking, sorry, I retreat. There is no noise frequency here. Forget what I just said, it would have held for a sine wave. But here actually I only have a single parameter, which is this sample and hold, because noise is always just random numbers. So with this one, you see, if I have a low frequency for the trigger, then I get a different frequency in an audible fashion, and then obviously, and then actually what happens, I start to get what I showed you earlier, which is actually noise modulation. Okay, so you can actually have this transition between, you know, just a melody-like thing into this textural sine wave thing and into a really noisy signal. And it's a continuum. Okay, so that's really interesting to understand that, you know, in sound synthesis, there is a lot of cases where you have a continuum technically, because it's a single parameter going from 0 to something, but perceptually you have distinct regions where you hear a totally different sound, essentially. Okay, so the same thing holds for granular synthesis as well, which you probably won't go into because it's, you know, here we are about the fundamentals. You can play with lovely synths in your own time. But the point is that, for example, and this is again a bit advanced, but I'm happy to kind of, you know, throw it in the air. If I'm processing with delay, okay, so I have an effect, an audio effect with a delay element in there somewhere, you also get something similar, because if I process with a delay which is the shortest possible, which is one sample delay, actually you can interpolate, you can get a shorter delay, never mind, but really short delays of only a few samples, what I'm actually doing is I'm filtering. If I'm processing with the delay between extremely short and probably 50 milliseconds is a good boundary. So let's think about it. So actually 1 millisecond, how many samples? How is your math? Your math, you're the best in math here, yeah, I imagine. So in 1 millisecond, how many samples do we have on a standard sample rate? So 1 millisecond is 1,000th of a second. Standard sample rate is 44,000 samples per second. Divide by 1,000, about 44. 44.1 samples in 1 millisecond. Okay? So actually I should probably go down to maybe even half a millisecond. So let's say from half millisecond, from about 20 samples until, let's say 50 milliseconds, if you change something, if you make an effect with the delay in this range, you're actually going to change the spatial impression of the sound, right? So in the shortest range, you just filter it. In the mid-range, you change the spatial impression, and everything above that, you actually start to detect a second event. So you actually get into a rhythmical domain. So we have rhythmical domain, we have spatial impression domain, and we have filtering, which is spectral domain. So for the technical, background, it is a continuum. From 0 milliseconds to a few seconds, it's a continuum. But for us, because we have this neurology, this kind of perception, it is three totally different things. Spectrum, spatial impression, rhythm, totally different things. Okay? So a similar thing that I like to say as well, we normally think that time and frequency are separate concepts because frequency comes in here, time is here. It's obviously very distant, they have nothing to do with each other. Technically, they are interrelated. You cannot separate them apart. Time and frequency are essentially two sides of the same coin, technically. You see? So that's really interesting. That's why signal processing is my favorite thing in the world after drumming, probably. It was my favorite thing until the age of 30, probably, and then I converted, but it's still my second favorite because you actually have to think in a different way. And the other thing which is interesting to say is that sine waves don't add up like apples. Because if I have two sine waves of the same frequency and I add them together, I still have only one sine wave. You see? So, and that's why I think it's really important to really dig these fundamental things up and solidify your understanding because it allows you to start thinking in a different way. Right? Because, you can be a musician and think in a musical way and practical way, you are turning the knobs and blah, blah. But if you want to do that, you don't sit here, you sit in the studio. So I assume you're really interested to know some more detail there. And if you learn this, you develop a totally different intuition, a different way of thinking. You see, because actually, for example, if you think about what's on the screen now, we were talking already about what happens with multiplication, right? So hopefully you understand the three things about it. And now you see that actually range conversion also has a multiplier. So this is, that's where the things may start to connect. And once you, start to understand these things, you can actually come up with really interesting new synthesis ideas. And if you don't, then you will realize that you think you have a new idea and you try it and it sounds the same. So that will be your testing method to see, do I actually understand? Because it's just a bit more interesting than I have user-friendly devices that I can connect and I make some fun sounds. That's fun, but this is the real life, this is the real thing. And that's why I'm saying, just so you know that, it's like a new start, it's like a new life. You have a new life now. Nothing will ever be the same again for you, okay? Okay, cool. Any questions? Cool. So I will now continue a bit. I'm not even sure. Are we scheduled for 1.5 hours, yeah? Or 2 hours? 2 hours. Okay. So probably worth having a break. We will have a break because otherwise. So before the break, the last thing that I want to show you is still FM, but it is a way of devising user-friendly parameters. Okay, so I've already spat on user-friendliness a minute ago, and I'll probably keep doing it, because unfortunately, a user-friendly object will never become a musical instrument. You have to have a lot of challenge and a really, everlasting learning curve to have an instrument. If I have a fader, after, I just cannot develop a better technique. There is no learning curve in the fader really. So it will not become an instrument. Although it depends on what you are fading. You might know, I don't know, you probably don't, but there is a tradition. So I talked about the German tradition in Cologne of sound synthesis in the 50s. They've started it pretty much. Meanwhile, in Paris, they've started the musique concrète tradition, So they were actually playing with recorded sound. So in both, you probably heard this, yeah? So what you then have is essentially, I was talking about user friendliness here. So the point is that in the musique concrète tradition, they used to do diffusion. So you would have an inverted mixer. So you didn't have 16 inputs and 2 outputs. You have 2 inputs and 16 outputs. And then sending to 16 speakers. And then they would, in real time, play with the faders and actually, shape the spatial playback of the music in real time. So actually they have developed faders to be an instrument, but then it's typically at least 10 of them, and it's a very specific interface to a specific process, which means that, you can actually spend a few years practicing, learning how to make it sound like this, make it sound like that. So you could make an instrument from a fader, but fader in itself is not an instrument. So every user-friendly thing is unlikely to become an instrument. So we are actually looking for user non-friendly things. But in designing sound synthesis and audio effects, typically you work for the user, right? And the case is that on the lower level, what you're looking at here, there is an increasing number of parameters. In 10 minutes, I could probably give you 6, 7, 8 parameters, all kind of working around this patch. Now, typically, these technical parameters that are available here on the screen are not the most user-friendly ones, are not the most intuitive things. Many things might happen. Maybe one parameter makes only a small change in sound, another parameter makes a large change in sound. Maybe within the single parameter, one region, first half, does a small variation, the second half does a huge variation. That's also typically not what the user would expect. So after figuring out the synthesis bare bones, as they say, the skeleton, what it actually does, typically a lot of time needs to be spent with designing the user parameters. Okay? So I will show you the standard user parameters for an FM synth. Okay, because here, actually, what we would have are following parameters. So I will call this the modulation frequency. So you've seen in the earlier patch, it was just the sine wave frequency, but now it's a sample and hold frequency for the noise signal. But it's kind of similar in the way that, it still kind of works. It's 2 hertz, means that I will get the noise value 2 times per second. Then I have another parameter here, which I didn't expose, which will be my carrier frequency. Oops, I don't have to look at the screen. I have to remind myself. So this is the carrier frequency. Why is this the carrier frequency? Because this signal, this is the carrier frequency. So this signal is bipolar. It's the modulator signal, -1 +1. I scale it up, in this case -1000 +1000. This does not affect the range, right? It just takes a value from the original signal. It does not change the value. It just removes a lot of them, essentially. So here, I'm scaling it up, and it's still a bipolar signal. So the modulator here will be centered around 0. Now, if I add 1000, then the modulator will be centered around 1000, right? So that's the carrier frequency. This is actually the frequency of this oscillator if the modulator is 0, right? So if I take down the modulator, and it doesn't go wee, it just goes a fixed frequency, it will go at this fixed frequency. Because the modulator will be 0 plus the carrier frequency is that frequency, that's what you hear. Okay, so that's your carrier frequency parameter, and then there is one more, which is my modulator depth, or modulation depth, I should say. Modulation depth. Okay, so the depth here, obviously you understand the depth, it's actually the scale. But if you think about how much it modulates, it's kind of depth, right? So I can actually, if I have a 1000 here, I have a lot of modulation. Maybe this is interesting to hear as well. Right, so I start with modulation depth 1000. And then I can decrease it. And I get a sine wave at 1 kilohertz. So actually, you see at this stage, both of these parameters kind of reduce the complexity, reduce the noisiness of the signal, but they do it in a different fashion. And if you want to connect a keyboard, like a piano keyboard, if you want to play pitch stuff with this, then it's all about the carrier frequency. So that's how you would essentially make a synth out of it if you wanted a kind of a keyboard-based synth. Okay, so those are the 3 technical parameters of frequency modulation. And now I'm going to show you the intuitively better parameters. And I don't even have to code it because we have a patch called Simple FM. And here inside you can see it. Oops. So, the user-friendly FM parameters, stop that. The user-friendly ones are the following. Carrier frequency stays the same because it's your input for the pitch. Harmonicity and modulation index. And you see there are 2 multipliers there, extra. And you see how they're kind of interconnected, these new parameters? Huh. Why? Okay, so we're going to take a break now. And you have 10 minutes to think about whether you want me to explain this or not.
Can you repeat, please?
Huh?
I don't get it.
I didn't explain it yet.
No, in the question.
So the question is, do you want me to explain this? It's 3 of you, so we can do a voting system. 2 against 1 wins. Because it's getting complex. Obviously, you know, we are using the time. Time is very precious because I'm here seldom. But if you think, okay, I really want to get to the depth, you know, I want to understand the stuff, then it's really good if I explain you this, even if, you know, you have to listen on the video once more and, you know, try it yourself. Or you say, no, let's just have more funny sounds, which is also a valid request. So let's take a break. And after the break, you will let me know what you prefer, okay? So we have the verdict, which is do the explanation. Okay, so you've actually already seen me do something when I increase the modulation depth. So what you read here, it says modulation amplitude. I've actually said something like modulation depth instead there. So we can actually, maybe easiest thing is to first just see what's happening, okay? And then we will try to explain why that is happening. So the first thing is that my modulation depth, can I correct this? No, it's locked. So my modulation depth is now much more complex, right? So I don't have a direct access to modulation depth, but instead, this is the product of carrier and the harmonicity times the modulation. Okay, so this should be apparent just by looking at it and understanding the basics of multiplier, input, output. And the other parameter that has disappeared is modulation frequency, which is something that comes in here. So, I mean, first of all, if you see this patch, if you see these 4 elements, those are the same 4 elements. I mean, this is a different oscillator, but it was the same thing. One oscillator, multiply, add another oscillator. So that's the same structure, right? So the only thing is these 2 extra boxes, multipliers, that change the way the parameters are controlled. And this input here is the modulation the modulation frequency. And what you see here now is that it is not directly accessible, but instead it will be the multiplication between the carrier frequency and the harmonicity ratio. So that's the new parameter. Now, the reason is that if your harmonicity, let's just experiment with this. I will show you. First, I will show you how the harmonicity works, why it works. Why can we actually produce a parameter that's called harmonicity? So in order to do that, I'm just gonna get rid of the sample and hold. That was fun while it lasted. And get to the original FM structure here. Okay, which looked a bit like this. I have a modulator, I have range conversion, and I have a carrier. So if my carrier frequency is, let's say, 2000 hertz, and my modulation is 200, then actually what happens, you see, I get sidebands. Can you tell me which sidebands I'm getting here? You see, they're kind of convoluted, they're all together, you don't quite separate them. But what are the sidebands? What are the frequencies in this case?
1800 and 2200.
And? That's the first order sidebands, which are always there, both AM, RM, and FM. But with FM, we get higher order sidebands as well. So definitely 1800, 2200, but also 1600, 2400. Those are the second order sidebands. Also 1400, 2600, third order sidebands. And so on until infinity, except that they kind of disappear in the display. Okay? So what does that mean? It actually means that some of these, that actually I will get a sideband at 4000 hertz. Right? Which is the octave on top of 2000. If I do something even more weird, if I say, how about I take a modulator frequency of 2000, I get this. So first sideband here is 0, here it's 4000. So it's actually bang on the octave. If I take 1000 modulation frequency, you see? So actually now the second order sideband is actually the octave. And the interesting thing is now, if I increase the modulation depth here, you see what happens is that the sidebands increase in volume, but they're not moving around. Okay? So if I have these parameters, that's what happens. The sidebands move horizontally based on the modulation frequency, and they move vertically based on modulation depth. Now, if I increase this, right, then I have actually a really interesting signal, because my fundamental frequency is 2K. I have the octave at 4K, which is the second harmonic. I have the third harmonic, but I also have something in between, right? Because all of these are spaced 1000 hertz apart, but the harmonics would be spaced 2000 hertz apart. So every other is bang on the harmonic. So actually this is a very harmonic spectrum. In fact, it sounds like a single sound source, right? Although there are extra spectral components which are not harmonics, still to our ear, well, actually, if some of you is a musician, you have perfect pitch or anything, or you can sing well, you can probably sing 2 pitches on this. You might be able to hear 2 pitches. If I give you a piano, you might be able to find 2 pitches that work. But that's psychoacoustics. We will study this at a different occasion. Now, the interesting thing is that if I just change this by a little bit, you suddenly get a clear sense of multiple sound sources. It's already a harmony. So what happened there? Not much. So instead of these sidebands being 1000 hertz apart, which allow them to be bang on the harmonics, now they are 917 hertz apart, so none of them is on a harmonic. So you see, that's the point, that with an FM you can get a harmonic spectrum, but you can also get a dissonant spectrum like this. Okay? Now, the funny thing is that if I do, for example, let me do 1500. You see, this again is a harmonic spectrum. I mean, it's not bang on certain harmonics, because now actually it takes 3000, but there is a harmonic relationship. There is a simple harmonic relationship. In fact, it's the relationship of a fifth, 3/2 ratio. And it's a harmonic spectrum. It almost sounds like an instrument. And again, if I just slightly change it, you already hear that it's like different tones. It's a dissonant spectrum. You see? So actually, there's a lot of values here that give you different spectra. But once you go bang on 1500, you see it cleans up. And if I go in the other direction, same thing happens. It gets more complex, it gets more like a chord. And then at some point again, well, here it's already a bit cleaner, right? But then it again gets dissonant. And there will be something in between, but definitely when I get to 1000, it cleans up. Okay, so that's the character of the modulation frequency parameter. So it's not like a continuous thing where it's increasingly like something in a linear fashion, it is a parameter which has these peaks whereby you get a harmonic timbre. And that is the issue. That is the reason why we are trying to devise a different parameter, which is called harmonicity, such that we can control the harmonicity in a linear fashion, in a more natural fashion. Okay? So that's one issue with this set of parameters. The second issue is that if I get, let's say I have this harmonic spectrum with a bit of a beating there, which is nice. And now I'm connecting this to a synth, and I suddenly play a different note. So what happens there is that the timbre of the instrument changes as I change the pitch. Because when I play 2000 hertz, it was a harmonic timbre. And if I play a different note, it's likely inharmonic timbre. So it's not a consistent instrument. You see? So those are the issues with these technical parameters, which is modulation frequency, which is this one here, and the modulation depth. So modulation frequency, to resume, has points where it becomes harmonic, points where it doesn't, which is not linear. And the modulation, essentially the problem, the other problem is that the instrument will change timbre if you change the carrier frequency. So actually the solution is such that these things are avoided. Okay, so let's see how that works. I believe this will be the carrier frequency. This is the harmonicity ratio. So the carrier frequency stays the same. This will be my harmonicity, and this will be my modulation index. Okay, I can just take these. Oh, I can't. So what will happen here then is, let's start with the same example. So I have a 2000. And actually, oh, sorry, I have to, these are, it expects the signals. You will study maximum speed at some point and hopefully get these things. But I won't go to any detail now. I just have to convert numbers to signals. May it be sufficient to say that. By the way, Balazs is happy with me teaching this with max MSP. You don't have to do Super Collider. Okay, so this is now the harmonicity. So if I take the harmonicity to 1, to 10, to 20, okay, I'm getting different timbres. And actually, let's watch the spectrum of that as well. Right, so the point is that now if I change the carrier frequency, probably need a bit of a lower modulation index just to have a cleaner thing. Okay, so now actually what happens, this is a bit extreme like that. Let me take a 0.5 here. Okay, so this you see what happens is that the timbre stays the same independent of changing the pitch. Right? And if I change the modulation index, I'm actually introducing higher order sidebands, but it's a robust thing in terms of the carrier frequency. Now, actually what happens now is that if I have an odd number here, you see I get a dissonant spectrum, but actually this dissonant spectrum is robust You see, it actually behaves more like a single instrument. Because what's happening is that essentially the modulation frequency, which is here, depends on the carrier frequency. You see? Because in the patch where I directly control these parameters, it does not relate to the center frequency, which means that sometimes it's harmonic, sometimes it's inharmonic. But here what happens is that the harmonicity ratio is actually the multiplier between the carrier frequency and the modulation frequency. So if this is 0.5, the harmonicity, then the modulation frequency will always be the half of carrier frequency. You see? So you're linking the modulation frequency to the carrier frequency, and by doing this, you will always preserve the same type of spectrum regardless of the carrier frequency, because it's the ratio between the two frequencies that determines the amount of harmonicity. And if the ratio is fixed, then you can freely move the carrier frequency, freely play a different tone, and you will always get a consistent timbre of the instrument. Okay? And then the other thing that happens here is that if I had a direct access to modulation depth, which is this parameter here, then also depending on the carrier frequency and the harmonicity ratio, thus the modulation frequency, the level of the sidebands would change. Again, it would give me a different timbre for a different pitch on the keyboard. And it's the same trick. I am making the modulation depth dependent on the carrier frequency. So you see it's all multipliers. So the higher the carrier frequency, the higher the modulation depth will be. And this is the exact amount of increase needed to maintain the level of sidebands. And therefore I get a consistent thing. I mean, I can try to demonstrate that as well. So if we go back to this one, so here I have these parameters separately. Okay, so observe the level of the sidebands. Okay, and now I'm gonna take an octave on top. So this will be 2346. You see, actually you get a different level of things. If I do only 1000 here, you see, in relation to the fundamental, the harmonics have a different slope. In some case they are higher, in this case they are lower. So again, this means that if you make a keyboard instrument based on this, the timbre will change for different notes. But in this case, it won't, as I showed you, right? So actually, you see, it's kind of convoluted because, why exactly? So it probably needs to sink in, I don't expect that like, oh, I understand fully. I don't expect it at this stage. But actually, the trick to learn something is to be puzzled. If you're not puzzled, if you don't desire to understand something which is difficult, you will forget it anyway. If I give you something simple that you can remember, it means you won't remember. But if I give you something which is difficult and puzzling, and next week you'll be like, I'm still not sure about this, that's great. Because that's a recipe to actually learn it. You know, the longer it takes for you to understand something, the more it will stay forever. You know, the more it's challenging, the better. But the important thing now is that you just get the surface level understanding. That I expect. So what we've done is we've made a more consistent instrument. That's one thing you have to remember. Second level is, how did we do this? Well, we played a bit with the parameters. Also should be easy to understand. Third level down is what we've done is we've actually looked at how one parameter controls the amplitude of the sidebands, the other parameter controls the distance of the sidebands, and we realized that this will change with the carrier frequency, with the pitch. So, and then the deepest level, which I don't expect you to thoroughly understand, is how this is done. How is it possible to make these three parameters into a different set of three parameters? In fact, just the two, right? So it's the modulation frequency and modulation depth become harmonicity and modulation index. So how these parameters are changed such that we maintain a consistent instrument. Okay? Great stuff. Cool. So this is, I mean, there's quite a few, maybe it's worthwhile discussing a few more low-level things. How is your brains, guys? Hurt? No hurt? A bit of hurt?
Hurt.
A bit of hurt. So we have the option to just, go for lunch. Because what I will do, I have these, I've explained this in different lectures already. There's a lot of videos on my channel that you can look at. And the next step will be filtering to understand. Shall we or shall we not, huh? I'm thinking maybe there is something which is a kind of a small addition here. Let's just add one small thing, okay? And then I will ask you to watch the filtering lectures online. Or maybe you guys can tell me what would be the next thing in kind of basic synthesizer design. Obviously, connecting the keyboard is a good thing to do, but I'm not so horribly interested in that right now. But in terms of a basic synth, we have oscillators, fine, in FM, great. We could add some filters, which is fairly straightforward. Because, I mean, using filters is not an issue, obviously. Understanding filters is a bit more complex. But maybe just to, kind of keep it simple to finish it off, what I'll just do is I'll just add in a filter. I mean, actually, yesterday I've added one as well. I'll make a low-pass resonant filter at 500 Hertz. Just so you see, because actually, you see in Max MSP it is quite straightforward. Things connect fairly intuitively to start with. And then what you expect is you see some parameters here for different inlets. This is cutoff frequency. This is the resonance. So now I get this kind of resonant filter there, and I can change the cutoff frequency. But you see, as I change the carrier frequency, it actually sounds like a different instrument, so that's what we've just fixed. So what do we do on top of this? How do I make a snare sound out of this? Maybe that's a good thing to end with. How do I make a snare sound out of this?
ADSR.
Envelopes. Okay? So I'll do this. That's, theoretically not very complex. I imagine you guys have used envelopes already. Yeah? You understand what it is. So I'll just do a quick envelope. And while I do that, there is something else, because it still won't be a snare sound. So I give you the time to think about this. in the meanwhile, so actually the simplest thing to do is a line. And the way we apply an envelope is by multiplication. Okay, so I already shown you that if I multiply with a fixed value, it's a gain control. If I multiply with a slow signal, that slow signal will determine the gain. So an envelope is a slow signal like that. So what I'll do then is apply this envelope to control the amplitude. Okay, you probably know by now that I could apply the envelope to any of these parameters as well. I leave you to play with that on your own. And here, actually, the way the line works is by getting a list of values. Maybe this is a good one. I can just copy it. I mean, if you get into Max MSP, you know, there's millions of tutorials. Other colleagues will be teaching using Max MSP slowly but surely. It's supposed to become your tool of choice for kind of low-level stuff. So I won't go into that here. I'll just say that this is an envelope. And this envelope is such that it starts at 0, goes to 1 in 2 seconds, and goes back to 0 in 2 seconds. So what I'll do is I'll just make a really short percussive envelope, which goes to in 20 milliseconds, it goes to 2000 to 1. Okay, so I'm trying to make a snare sound, and I think that this is still a bit too long. So I'm gonna change that back to 1000. But it still doesn't sound like a snare. What do I do?
Add some noise.
Now, obviously, I could add noise separately, but the interesting thing, the reason why I'm showing you this, is that I can actually insert noise and replace some of the oscillators with a noise oscillator. What you've seen me do at the beginning, I've actually taken a sample and held noise for any of the oscillators. So let's do that again. So then this means that I don't have a cycle here anymore. I have a noise. In fact, I have a sample and hold, which takes this frequency. Okay, so the sample and hold becomes my modulator. This becomes the actual triggering frequency. So I need a sine oscillator. I could do another oscillator as well to trigger the sample and hold, like that. And then I have a noise signal that I'm sample and holding. So what I'll do here as well, just to show you a few more things that you will learn a lot about at some point. I put in a metronome to actually play this thing for me because I don't want to be clicking it. Okay, it's a bit too fast because the envelope is so long. Okay, and then I can figure this one out. So what I'm saying, I have a noise. Okay. Oops. Okay, so it does get a bit noisy, but it still sounds a bit like the 60s. So if I increase the depth, maybe decrease this. The depth is already such that I don't really... And probably this low-pass resonant isn't very useful either. I need it snappier, yeah? I need this to be shorter. So maybe 400. Okay, so I can still play a bit with this. So if I decrease the rate of the noise, you see it gets kind of more granular. And if I increase it, then I can get to this. Nice little noisy thing. And if this is so high, then actually these parameters won't do as much. Obviously this, if I decrease, again, I have a way of reducing the complexity. Okay, which is actually really good, because in this case, this could be the setting for a ghost note for low velocity snare, and this could be the setting, this could be the setting for high. Because actually, you see, the high frequency content also increases, so you can do something like that. And then the modulation depth, increases it even further. But if I go back here now, you see I'm losing that kind of depth, and I can actually get to a hi-hat type sound as well. Okay, so that's your basic envelope. So I think that's plenty for today, okay? So I cannot save this because I didn't fix my license, I believe. Can I save it? I can probably paste it into a Max for Live device and then save it as that, but I won't bother, because if you are interested and motivated, you can watch the video, and as you watch it, you can patch it yourself, which is, I think, a good learning process at this stage. But as I said yesterday, your exam will be theoretical. The second half of this module will be practical, when I will ask you to make music and sounds. In the first half, I will ask you to study the theory, okay? So I've shown you a lot of things just to make this theory a bit more accessible, something to relate to in terms of timbre. But actually, it won't be part of your exam to do anything in Max MSP, right? And in the video from yesterday, you can see all the options, how you can take an exam. I have about 5 different options for you. And if you think of a new option, I'll probably be happy, because I'm not about, making uniform brains. I'm not interested in uniformity. I'm interested in, brilliance. Okay? So thank you. And we can talk about when you think is a good time for, I'm thinking maybe every 2 weeks we can meet on Zoom. What I will do then is I will send you a video lecture for the 2 weeks that you should watch, and then on Zoom you can ask questions. Okay, that's when I can, relate to, or, I'm happy for everything. If some of you already wants to start coding Max MSP, you can bring in a patch. This doesn't work, please help me with this. So it will be more of a consultation thing, because the lectures are there. So just, you can watch them whenever you like. You can watch them twice, You can watch them double speed if it's boring, that's up to you. And then I think, you probably don't have a preference. Is there any days? It should be an evening slot, maybe around 6 or something like this. Any day is good for you guys, I imagine, or? Evenings.
Not really good, but the days,
Evenings are not good for you?
Yeah.
No?
Trainings.
I can do like a noon slot as well on given days. What's the best? Do you have any constraints? The reason why I'm saying evening is because you might have other classes in the day here.
Evening is good for me.
Huh?
Evening is good for me.
Evening is good for you. So then you have the only constraint, so you can let us know what is the constraint, and then we can schedule it to fit it.
Okay.
Yeah? So I will send you emails about this, and then take it from there.